Well, in the next, let us discuss a little bit details about the last piece of the proof of the generalization risk, where we establish that when there is a breakpoint for a hypothesis family, that means there exists some integer k. When there are k data points, the hypothesis cannot generate enough hypotheses that completely cover the all possible 2 to the power of k dichotomies on the k points when they are generically arranged in the data space. To prove that, when there exists such a k, then for any number beyond the k, the maximum number of dichotomies for the hypothesis H to generate n data points when n is greater than k is polynomial on n. To establish this result, we introduce an auxiliary quantity. Let's call that B n k. This refers to the concept that if there is a breakpoint, if in case in here the breakpoint is a misnomer, which means let us accept the assumption that there is no k points can be completely covered, can be shattered, where there are no k points on which we have exhaustively take the 2 to the power of k dichotomies. So no such completely coverage of the dichotomies for any k subset of points. When this is the condition, we are considering the maximum number of dichotomies that could be associated with n points. Note that this is the maximum number of the dichotomies, but this is not a maximum number of any particular hypothesis family H. So this is upper limit because it's exploring whatever kind of combination of the dichotomies on the n points without referring to any particular hypothesis family n. So for any particular hypothesis n, if it has a breakpoint of k, then the maximum number of such a hypothesis could generate on n points is up limited by this number, the bnk. Bnk is agnostic about the hypothesis family. So let's consider this upper limit. We will use mathematical induction, and we will consider the relationship of B and K and the same quantity of a lesser number of a simpler combination. Let's assume some dichotomy set on the n points realizes the BNK. So in the imaginary world, we list all the dichotomies in all the BNK dichotomies in a list or in a table. See, without loss of generality, let's consider the last data point. Let's consider both the last split data point into the last one and the first x1 to xn minus 1. So we group those dichotomies as follows. we consider the realization of dichotomies in the first n-1 points, these columns. So there are two possibilities for the dichotomies on the n-1 data points. The dichotomy can be a singular one, which means you can have only one copy of such a dichotomy in the first n-1 points. And for the last data point, the classification can be either positive or negative. On the other hand, the first n-1 dichotomy can be duplicate. It's not singular, it's duplicated. There are two exactly the same dichotomies on the n-1 points. And in this case, there are two copies of the two dichotomies with the classification at the last data point to be both positive and negative. So we have two copies of this n-1 dichotomy, and as to the last data point, in this set it contains both the positive one and negative one. And remind ourselves that this table satisfies the condition that no k subset of the columns, you cannot find k columns, and the k columns contains all the 2 to the power of k possible dichotomies on the k data points. So that is our assumption. So let us call the subset of the singular dichotomies, n-1 dichotomies, as alpha. We use alpha, we abuse the symbols a little bit and use alpha refers to both the set of dichotomies and the size of the set. And we refer the two copies of the n-1 dichotomies with both the positive and negative classification for the last data sample as beta. So now we have our bnk to be represented as alpha plus beta plus beta. So our key observation is that the sum of alpha and beta, if you consider these two sets when they put together, this must be less than b n-1 and k. This is obvious. In this sub-region of the table, we cannot find k columns, and the dichotomies in the k columns exhaust all the possible 2 to the power of k possible dichotomy possibilities. If we can, then obviously that k columns apply to the entire table as well, and then we will not be discussing this number b and k because the k columns will violate our condition. And more interestingly, let's consider the last beta set, and we have the conclusion that the beta set must be smaller than b n-1 k minus 1, which means we cannot find k minus 1 columns on which we can exhaust the all possible 2 to the power of k minus 1 dichotomies. Because if we could And we know that this subset represents the duplicated subset of dichotomies, and if from this part we can find k minus 1 columns where the full possibilities have been realized, then we can add xn as another column, and with the 2 beta, this region, because xn, because in this n minus 1 columns, these are 2 duplicate. Well, if the k minus 1 points on the k minus 1 points, all possible dichotomies is realized, it has been realized twice, with xn to be exhaustively set as positive and negative. And from this region, we then constructed a k subset on which all possible dichotomies has been exhausted, which violate our condition for B and K. So, well, I think I have misplaced this symbol here. Let me correct it. So we have this relationship of Bnk and B n minus 1k and B n minus 1k minus 1. So if we first place those trivial B1k and Bn1 in the table, for any Bn1, the maximum value of dichotomies is 1, because the condition is that there is no one point on which we can have both classification possibility on the one point. There are only 2 classification possibilities on one point, and we cannot realize all the 2, so the maximum number of dichotomies we have on the endpoint is just 1. And on the other hand, if we have only 1 point, then the limit of k is irrelevant when k is greater than 1. So we can have 2 possibilities. Well, establishing these 2 one row and one column of the table, we can progressively work out the upper limit for any B and K. So our conclusion about the polynomial bond can be derived from this relationship. To be convenient in the derivation, let us reform the relationship in this way. So now we are considering the relationship of B n plus 1 and K, and that is uplimited by the sum of n K and n K minus 1. We use mathematical induction. So to establish this, we consider this item is less or is upbounded by the sum of this. Note this sample represent to take I elements without replacement from n. And on this part, the second item is bounded by this sum. We do a bit reorganization of the sum. So we let them to start from I equals 1, because when I equals 0, there is only one possibility of taking 0 element from n, that is 1. And we move the summing variable I one level up, one element up. So we are now aligning the sum of these two series, and we take the relationship using this one, because when you take I items from n without replacement, this possibility, and you take I minus 1 items from n, these possibilities, when they put them together, is equal to the number of possibilities of taking n plus I items from n plus 1. That is because you have two possibilities of doing this, either to include the last item, this plus 1 item, then you take I minus 1 item from n, or you don't use that last item and then you just take I items from n. So the number of these two possibilities equals to the number of possibilities of performing this. As we have said, 1 equals the possibility of taking 0 element from whatever number of elements. When we put this together, we arrive at this relationship. And as we first discussed, because B is agnostic about the hypothesis family, so when we take into the consideration of any particular hypothesis family, this number is upper bounded by B. Then let's remove this plus 1 from this equation, and we get what we have desired representation of the upper limit of the number of ways to generate dichotomies on n data point when there is a breakpoint for the hypothesis set, which is polynomial with respect to n. So this provides the last piece of our proof of the generalization risk of learning.